Last week, we talked about some of the things we don't like about the standard model of particle physics. This is our explanation of three of the forces of nature and how we don't like how we have to plug in some numbers by hand. And there are some things we don't understand, like the neutrino mass and the nature of dark matter and why the Higgs boson is the way it is. We have this fantastic, complicated machinery of the standard model, but there's some things, that we wish were different, that we wish were a little bit better. And that's one of the motivations for a new theory for something like string theory. The other motivation comes from the fact that the standard model only describes three of the four forces of nature. Standard model describes perfectly well electromagnetism, strong nuclear and weak nuclear. But then there's gravity. Gravity is like in its whole other ballgame. It's just a completely different way of describing the universe. In the standard model, everything that we see, electrons and photons and Z bosons and all this, these are fields. These fields soak and permeate all space-time like oil and vinegar do inside of bread. And they're always wiggling and jiggling and doing all sorts of stuff. And every once in a while, a little piece of the field gets an extra excitation. It gets a lot of energy, and we call that a particle. But it's all fields playing on top of space-time. General relativity, however, is the story of space-time itself. In the standard model, the fields are the actors and then space-time is the stage. General relativity, our description of gravity, says that the presence of matter and energy bend and warp space-time, and then the bending and warping of space-time tell matter how to move. In general relativity, space-time isn't just the stage, it's also an actor. Completely different description of reality, of just a completely different viewpoint. Like it's an entirely different language of describing all this stuff. Now, a lot of introductions to string theory and discussions of string theory talk about the fabric of space-time, how general relativity says it's smooth, but then in the quantum picture, when you zoom in on very tiny, tiny scales and you look at the Planck scale, there's this rolling foam and everything. I mean, that's correct, but that's not really the source of the difference of why we have trouble reconciling general relativity with the standard model. We have trouble reconciling our theory of gravity with our theories of all the other forces because gravity just doesn't like quantum mechanics. All of our theories, the standard model, these are based on something called quantum field theory. Sorry, had a blank there. Quantum field theory forms the basis of our standard model, and this is all quantum mechanics. It's like all baked in quantum mechanics. And when we try to apply the exact same rules that we do, the quantum rules of the universe, and apply them to general relativity, it just falls apart. And it falls apart. If you remember last time, I was talking about when we have to go to do calculations in quantum mechanics, say two electrons bouncing off of each other. We have to add up, we have to include every single possible way that those two electrons could possibly talk to each other. And this introduces a lot of infinities, but we have some techniques for taking care of that. We're not too proud of the techniques, but we do them anyway, and it works. Once you add gravity to that, once you add the character of space-time and the fact that space-time itself can change, when these two electrons interact, the space-time between them can take various configurations and arrangements, and we have to include those. And so, yeah, there's an infinite number of possible ways that the space-time between the two electrons can change as the two electrons are interacting. But our tricks don't work. There are too many infinities. It blows up. We can't wrestle it back all in and corral it and try to coerce it into giving us an answer. We just don't have that option when it comes to gravity. It just blows up. We get infinity every time we try. So every time we try to apply quantum techniques to the gravitational world, it just falls apart. And this process, this attempt at unification, this failed attempt at unification drives us nuts, because you can write down the equations, you can write down a quantum theory of gravity, and then it just doesn't work. And you're just staring at the equations, you're like, why don't you give me something useful? And the equations are just like, just looking at us. So frustrating. We feel that there ought to be unification, but nature is under no obligation to unify physics. It could be that there's just no such thing as a quantum theory of gravity, and we'll never figure it out. Let's not go there yet. We hope that there is a quantum theory of gravity. We think there is a quantum theory of gravity. In the vast majority of cases, this quantum theory of gravity doesn't matter. Here on the Earth, and even in collider experiments, we don't have the energies needed where quantum gravity actually matters. But there are some places in the universe, like, I don't know, the middles of black holes, the beginning of the universe, where quantum gravity matters, and we wish we could understand what's happening at the center of black holes. We wish we could understand what's happening at the earliest moments of the universe. Without quantum theory of gravity, we can't ever understand them. So, you know what? It's worth a shot. And string theory claims, and in some ways, many ways it is, a quantum theory of gravity. So starting next week, we're going to explore the origins of string theory. But I hope with these past 2 videos, you understand some of the motivation of why we care about string theory in the first place. Thank you so much for watching. Please go to patreon.com/pmsutter to keep these shows going. And like, share, subscribe, or don't.